Welcome to another fabulous day in Calculus 3, and we're going to do Stokes' theorem. Yeah, so what of it? Well, let's do a quick review. Do you remember greens? Sure you do. It's a big theorem, big powerful theorem. And greens is used when you're doing a line integral that's closed in the plane. So greens is only good for 2D, which is kind of a bummer, but hang on to that thought. And so you're given this line integral that may look like FDR, or it might look like differential form mdx plus ndy. Either way, you can apply greens if you've got a simply connected region and it's a nice simple closed curve and all that good stuff. And you apply it by turning the line integral into a double integral. And for circulation, you're going to have the ndx minus the mdy as your integrand. And we learned that the two-dimensional vector field's curl is dndx minus dmdy. And you dot product that with your k, which is, k hat 0, 0, 1. And that'll give you dndx minus dmdy. We did all that, where you embed the two-dimensional vector field into 3D by giving it a 0 third component. Fine. Now, what if you needed to use greens in 3D? Like, what if your curve wasn't in the XY plane? It was some really weird curve and it was closed. Could you do greens in 3D? And the answer is yes, you can. You can do Stokes. So this is the higher dimension analog of greens, called Stokes, named after the English mathematical physicist, George Gabriel Stokes. So you're going to give a relationship between a line integral and a double integral, but the double integral is going to be a surface integral. Yeah. So check this out. So here you have 2D, and you already know how to do this. This is review. You're doing circulation here. How would you translate this or jack it up to a higher level, adding an extra dimension into the conversation? And this is the way you do it. So your surface here is kind of like a capping surface. Now this surface that you have here in greens, you can think of it as a surface, but it's flat. It's the capping surface would be z equals 0, essentially. Okay, but what if the capping surface, had a little something to it, not just z equals 0? So you still look at the boundary of this curve that is going along the surface, the capping surface, and you use your right hand rule where your fingers are going in the counterclockwise direction, and your thumb is going to represent the direction of the outwardly directed unit normal vector n. Right hand rule, folks. That's this n right here. Your n is your thumb. So Stokes is going to take the curl like you had here in your greens and just copy that down. And instead of k hat, which is a unit normal vector 0, 0, 1, which is a unit normal vector to the z equals 0, you're going to replace that with this. So it's going to be like the jacked up version of greens. And this is what this says right here. You do need some criteria to be met. You need this oriented surface, unit normal vector n, bounded by a piecewise smooth simple curve C with positive orientation. That would be counterclockwise. And you got a vector field whose components have first partials. And you do your Stokes. Yay! And now let's do it. Okay, are you ready for your first Stokes? Oh, I love this. So I want you to look at what they're asking for. You can even see in the diagram. We're going to do Stokes, which is essentially greens, where the curve is going around counterclockwise, and it's made up of 3 piecewise smooth curves. So your curve is like C1 union C2 union C3, going around that triangular region. And the unit normal vector is sticking out from this plane here, which is kind of tilted at an angle. So that's your capping surface. So we need to get all the pieces here. Okay, so it doesn't matter what order you do it, but I'm going to first solve for z because we need our capping surface given to us as little g. So if you do solve this for z, it's not very hard. Just subtract the 2x and 2y terms from both sides. And remember, this is g. So your unit normal vector, or what you use for it, is going to be negative gx, negative gy, 1. You want it oriented outward and upward. So for us, you're going to have negative, and then when you take the partial of z with respect to x, I get negative 2. Oh, that was easy. And then negative, the partial with respect to y, I get another negative 2, and then a 1. So this is going to end up being 2, 2, 1. That's nice. And then we also need to get the curl of f, because if you look at Stokes, you got to get your curl. Now remember, curl is the cross product of the differential operator with your vector field. And I always like you to use the 3x3 determinant method to get it. So humor me and do this on your exam or your final or midterm. And so I'm going to put the components of this vector field 2y minus z, x, y, z, and then e to the z along the bottom row. And then I'm going to go d d y e to the z minus d d z x, y, z times I hat minus d dx of e to the z. I'm just basically doing all this stuff on the fly here. d d z 2y minus z j hat plus, see what we got here, d dx x, y, z minus d dy 2y minus z k hat. Woo! All right, what do we got? So this right here looks like it's going to be 0 minus xy times I hat minus another 0 minus negative 1 j hat plus d dx of xyz, I think is yz minus d dy of 2y minus z is 2 k hat. And if I clean this up a little bit and give it component form, because that's my favorite, it's going to look like a vector with negative xy, negative 1, and yz minus 2 as components. And remember, this is the curl of f. Yeah? Okay. We're getting somewhere. Now, doing even one Stokes problem, I won't lie, it takes a while because you got to get all the ingredients. You got to go get the normal vector. You got to go get your curl. Then you got to take the dot product of that and then set up your double integral. Okay, so here's what we're doing. We're doing a surface integral, basically, which is Stokes. And you're going to turn it into a regular double integral where you take the dot product of your vector field with the normal vector, like so. So let's go do this dot product and then we'll worry about other stuff later. So we're going to go negative xy times 2 plus negative 1 times 2 plus the expression yz minus 2 times 1 dA. Now this is a bit of a mess, but no worries. What do we have here? Negative 2xy minus 2 plus yz minus 2, another 2. So you can combine these minus 2s to minus 4. That doesn't help a lot. So what do we have? Negative 2xy minus 4 plus yz dA. Now, what do we know about z in a double integral? Not okay. You need to replace this with something because you're not allowed to have z in a double integral. In a triple integral, sure. But in a double integral, not so much. So what are you going to replace that with? The capping surface. Right here. You replace it with 6 minus 2x minus 2y. Okay. Really? Yeah. So 6 minus 2x minus 2y. So then what? Well, you know, the integram looks even messier now. I know. That's the way it is. And now I'm going to figure out, what am I going to do? Well, I'm going to choose dy dx as my favorite order of integration. But what is the region? Well, if you look at the projection of the capping surface onto the xy plane, I hope that you see, and you've done this before, it's going to be this little triangular piece down here. So that's our region R. So how do we get that? Well, if you set z equal to 0 in the plane equation, you'll see that what the trace of the plane is when you cut through the xy plane, because that's where z equals 0. And after rearranging your terms and then dividing both sides by 2, you get x plus y equals 3 as that diagonal line. So if you look at your region here, like this, this is your region R, okay? So if you solve for y, you get y equals 3 minus x. So your limits for y are 0 to 3 minus x, and then your limits for x are 0 to 3. So if you get this far, I'll give you partial credit. It's like, yay, you're giving the circulation around this portion of the plane going counterclockwise. So now what? Well, let's just do a little bit of hand-to-hand combat here, and then we'll kind of finish it out using our graphing calculator, okay? If I were you, I would distribute the y over the parentheses before you start your integration. Okay, so now what do you have? Oh, a big mess. I get 6y minus 2xy minus 2y squared. Now, you have like terms, and I'm just a big fan of combining like terms before I integrate, just to make my integration a little less messy. Not that much, but you know, it helps. Yay! So those combine to negative 4xy. So if we integrate with respect to y, ooh, we're going to get what? Negative 2xy squared minus 4y plus 3y squared minus 2/3 y cubed. Oof. And you're going to go from 0 to 3 minus x. Oh boy, this is starting to look just horrible. Yeah, I know. Because once you substitute the 3 minus x, oh my goodness. Okay, and then this is the part where, unless you like foiling a lot, you're going to go, oh, what a disaster. This is going to take too much time of my, exam. So use your graphing calculator using the FNINT menu selection and finish it out. Okay, so et cetera, or you could do it by hand. It'll take you a while. I get negative 18. Okay, that's your circulation, and that's your answer. That is the answer to this problem. And we're done. And that concludes this Stokes theorem example. So let's recap. What did we do? Hey, we're stoked. We found the circulation in 3D instead of 2D. So that the 3D version is Stokes. So we found the circulation. Now, what does that mean? Remember, for greens, the circulation means if you had that little paddle wheel with these little vertical paddles, remember it meant, if you stuck that paddle into your jacuzzi, it would spin, in whatever direction and how fast. Same thing, only now your jacuzzi isn't just sort of that flat plane. If you stuck your paddle in here like this, where it'd kind of be at an angle, it would spin. Negative 18 means it would actually spin clockwise, and 18 is not a bad number, so it'd probably be spinning pretty quick. All right, that's your circulation. Circulation flow around that triangle. Nice. Okay. Okay, so everybody's going to try example 2, which is very similar to the last example I just did. And you and a buddy are going to try this one, and I will wish you all the luck. And if you have questions, I'll come in and visit. See how that goes. For the folks at home, what we should be doing here is having couple of things like the last problem. You may want to first solve for z, which is your little g. So first subtract 2x and y from both sides, and then divide both sides by 2. And this is your little g, essentially. Okay, so now you're going to get your normal vector. It's actually the NDS portion, but I'm kind of killing up. So remember, it's negative gx, negative gy, positive 1, if you want an oriented upward normal vector. And so here you're going to have negative, and you may want to distribute the half before you take those partials, okay? So you're going to get a negative, and then here you're going to get negative 1, and then negative, what? Negative a half, and then 1. So your normal vector looks like 1, a half, and then 1. So now you got to go get your curl of f. So if you're going to do the I hat, j hat, k hat, ddx, ddy, ddz, and then put your, oh boy, I'm going to probably need more room. This is z plus x cubed sine x. Then we have e to the y, and then we have negative 2x here. Okay. So when you go like this, you're going to have ddy, negative 2x, minus ddz, e to the y, I hat, minus, then you're going to go ddx, negative 2x, minus ddz, it's a minus, of z plus x cubed sine x, j hat, plus ddx, negative 2x, minus ddz, z plus x cubed sine x, that whole mess, k hat. I think I did that right. Let's just double check. Oh boy, okay. Yeah, this one's wrong. This is ddx of e to the y, and then that is minus dy. Okay, make sure I get all those right. Okay, now what? Let's just go ahead and do these partials. So dy of negative 2x at 0, minus ddz of e to the y at 0. Oh, so we get 0 I hat. Minus, and then ddx of negative 2x, I get a negative 2, minus, and then ddz of that whole mess, looks like it's just going to be 1, j hat, plus, and then here I'm going to get ddx dy at 0 minus ddy. There are no y's in there, k hat. So if I put this into component form, there's my curl. Okay, so I have two big ingredients to apply Stokes' theorem. I've got my curl, and I've got my normal vector directed outward. Those are the two biggies of ingredients. So now what? Well, I'm going to put it all together and take a dot product. So my circulation is equal to this. This is what I'm doing here. Curl of f dot n ds. So turn it into a regular double integral. I got my curl of f at 0, 3, 0. I'm going to take this nds, which I got was 1/2, 1, and then dA. And when I do the dot product, my goodness, all I get is 3/2. Easy peasy. And it's just a multiple, so I'm going to pull it out. And then I have a double integral just involving 1. And you know what this is. This is area of the region. But what is the region? And if you look at the diagram they gave us, the region is this triangular portion here in the xy plane. So if you let z equal 0, you know, you're going to have 2x plus y equals 2. And so that's just going to look like this triangle right here with x-intercept is 1 and a y-intercept is 2. So you could just get the area of the triangle using your knowledge of areas of triangle, which is 1/2 base times height. So the base is down here, and it looks like it's a 1, and then the height is a 2. So it looks like the area of your triangle is 1 unit squared, or 1 square unit. So your final answer for Stokes is 3/2 times 1, which is 3/2. There it is. And we're done. That would be letter D. Yeah. So it's not too hard, right? So I'm going to finish doing one problem. I want to do a verify. And this is sort of the grand finale, and then we'll do a grand summary of all the vector calculus formulas. So how does the verify work for Stokes? Well, you know, you got to do the left-hand side and the right-hand side when you're doing a verify. Oh, man, what do you mean? It's another one of those crazy things. It's not as bad as you think, though. Let's just take a look. What does the left-hand side of Stokes even look like? It is one of those lovely FDR line integrals. Yeah. Okay. And this one isn't too bad. We do have to parameterize, though. Okay, fine. So the capping surface is a hemisphere where it's centered at the origin of radius 2. So if I were to graph this capping surface, okay. And the curve C is just the curve there in the XY plane. It's a circle of radius 2 centered at the origin. So this is the curve, the C. So if we are going to do the left-hand side, which is do this FDR line integral, then we are going to have to parameterize. Yeah. So what do we mean? Well, the R is not too hard because remember circles, you can use cosine and sine. So R is going to be 2 cos, 2 sine. Oh, we're working in 3D, so we better put a 0 here for our third component. And time is going to go from 0 to 2 pi seconds to go all the way around the circle. And because we're doing an FDR line integral, we're going to go ahead and get R prime, because you know, you're going to need that to do your dot product. And so then your FDR line integral here, you got your F. Now remember your F, what did they say it was? It was Z minus Y X. Oops, where are we? Here it is. Z minus Y X and negative X. So remember, you're going to take, you know, the Z minus Y X negative X. You're going to have to replace all those with what? Z minus Y for us is 0 minus 2 sine t, comma. X is just the X component from your vector value function. That's 2 cos. And then negative X is negative 2 cos. Okay. And then you'll take the dot product of that with your R prime. FDR. Dot product. dt. And time is going from 0 to 2 pi seconds. Fine. And when you take the dot product here, I get negative 2 sine times negative 2 sine. That's 4 sine squared. Plus 2 cos times 2 cos is 4 cos squared. And then negative 2 cos times 0, well, that's a 0. So who cares about that? And then you guys know a trig identity. If we factor out a 4 from this integrand, the other factor is sine squared plus cos squared, which is just 1. So you know, we just get one of these guys. And then we're going to integrate with respect to time t, which is just t. And our final answer is 4 times 2 pi, which is 8 pi. Okay? And we're done with the left-hand side. So that's the LHS doing the line integral. Fine. Now, what about the right-hand side? That means we're going to apply Stokes. This is a little bit tricky, so you're probably going to go, well, I don't like Stokes, but okay. So you have to get your capping surface written as solve for z. So if you try to get z, you're going to get the positive square root of 4 minus x squared minus y squared. And if I rewrite that so I can find the partials, I have 4 minus x squared minus y squared to the half. So why is that important? Well, it is. Because you're going to have to get that curl of f, and then you're going to need to get n. So I'm going to get n first. Remember, n ds looks like negative gx, negative gy, positive 1. So you got to go get those. And so you're going to need the chain rule. I know. So negative gx would be negative, and then when you take the partial derivative of that mass using the chain rule with respect to x, it's not going to be pretty, okay? Don't worry. And then negative gy, so negative, putting a negative in there now, chain rule, and then positive 1. Okay, when I clean this up and reduce and do all this stuff, and I'm going to put the, I'm going to use positive exponents and then replace with the radical. Okay, and then this should be, what do we get here? Hang on a second. So that should be what? X over, okay, yeah, that looks right. And then this one's going to be Y, the 2's cancel. And then a 1. Okay, so there's my N. That's, save that for a moment. Let me just change something up here. Yeah. I want you to notice something here. I know you're going to think this is like the wrong thing to do, but I'm going to do it anyways. Do you notice that both of these denominators are really the same as z? Because that's what z was. It was the square root of 4 minus x squared minus y squared. Yeah, I know, but so what? Just, yeah, you may see some of the solutions manuals. Sometimes they replace that with z. So you may or may not want to do that right now. It's not going to like change everything. Like, oh, is that going to change the answer? No. But sometimes it makes it easier to look at. So that's all. That's the only benefit. So it's not a huge benefit. Okay. So now what? Now you're ready to do this surface integral, which is using Stokes, curl of f dot product with this NDS business. So you're going to go, okay. You're going to have the, where the heck am I? Oh, I still need to get curl of f, don't I? So let me go get that. What is curl of f? Sorry, I forgot to go get that. I hat, j hat, k hat, ddx, dy, ddz, z minus y, x, negative x. Okay, here we go. Let's see, I'm going to have ddy, sorry, of negative x minus ddz of x, I hat, minus ddx negative x minus ddz z minus y, j hat, plus ddx of x minus ddy z minus y, k hat. Oh boy, what a wreck. Okay, so take the partial of negative x with respect to y, 0. Take the partial of x with respect to z, 0. Okay, nice. Take the partial of x with respect to, or of negative x with respect to x. That's not 0, that's negative 1. Minus, take the partial with respect to z of z minus y. That's going to be a 1. J hat plus ddx of x, that's 1, minus ddy z minus y, that's a negative 1. K hat. Oof. Okay, so what am I going to get here? In component form, looks like I'm going to get a 0, 2, 2. So that's my curl. All righty. Now, when I'm trying to put this double integral together here, I'm going to go 0, 2, 2 dot product with x over z, y over z, 1 dA. So once you take the dot product here, you've got a 0 times something, that's 0. 2 y over z plus 2. Okay, so this is what we're going to need to worry about right here, and that will get us the final answer. Now the problem is you're not allowed to have a z in a double integral, you know. So what are you going to replace the z with? Well, you're going to have to replace it with the 4 minus x squared minus y squared square root of, and that's a real hassle. And then the other thing that you may need to notice, and that's why I'm doing this problem, is what is the region? Well, the region in the xy plane is what? Remember, you've got your hemisphere there. So your region in the xy plane is this circle of radius 2 centered at the origin. So you know what we're going to do? We're going to convert to polar. Oh, yeah. So what does that mean? Well, you know, the usual conversion formulas, but what I'm going to do is this will be the square root of 4 minus the quantity x squared plus y squared, which we replace the x squared plus y squared with r squared. So what I'm getting at, I'm getting somewhere, is that the double integral that looks right now like 2y over square root of 4 minus x squared plus y squared, and then we have plus 2, and then dA like this. Once we convert to polar, you'll have 2r sine theta all over square root of 4 minus r squared plus 2, and then r dr d theta. I know. And then r is going from 0 to 2, and theta is going from 0 to 2 pi. Now, this, when you integrate, well, first you need to distribute the r. So it's like, oh, no. Don't get too excited. Hold on a minute, because we're going to look at something that's kind of nice. If you don't mind, I'm going to flip the r and the theta order. Well, why can you do that? When you've got pure numbers as limits, it's super easy. You just flip everything, okay? I'm going to show you, this is the one time where it's like useful to flip when you're doing polar, in my opinion. Well, how's that going to help me? Like, oh my God. Well, we're going to integrate with respect to theta first. So that's going to make it easier, because otherwise you're going to have to use trig sub on this, and I don't want to use any trig sub. So what is the antiderivative of sine of theta? Well, you know, it's minus cos, right? And then this is just going to be 2r theta going from 0 to 2 pi. And then after we're all done, we'll integrate with respect to r. Fine. So what you're going to notice is that this cos term, or factor rather, when you evaluate it on the full revolution going from 0 to 2 pi, you're going to end up with what? 0. Cool. I should delete this one integral. So this term goes bye-bye. Nice. So what about this? We're going to have 2r and then just 2 pi. And that's going to be the only thing left, is 4 pi r. And now you can integrate with respect to r. So the reason why we integrated with respect to theta first is I didn't want to try to integrate this first term with respect to r, because I hate trig sub. It's painful. So because the sine theta, once you integrate it, goes to 0 from 0 to 2 pi, made our life easier. No trig sub needed. Woohoo! And now we can finally finish out our integration with respect to r, and that's not too hard to do, you know, right? And I get a final answer of 8 pi. And isn't that what we got when we did the left-hand side, the hard way? It is. And so, yay, that concludes this problem. The verify was successful. So you just got to see an example of Stokes for you to convert to polar. So here's the big summary of a lot of integration that you've done over the last 3 semesters. Yeah, Calc 1, Calc 2, Calc 3, everything. So in Calc 1, what did you learn? Fundamental theorem of calculus. And in this class, we learned a different, basically extended version of it, fundamental theorem of line integrals. Yeah, that'll be on the exam next week and the final, don't worry. And then we looked at greens. So we did greens. And then we did an alternate version of greens, and they're not showing this other part. I'll show you. This was dm dx plus dm dy. That was the flux version. So this is the circulation version of greens, and then this is the flux version of greens. Please know both versions for the midterm and the final. And then the divergence theorem, and then Stokes. There you have it. That's the big old summary of this chapter. And the meme, the more complicated the math, the dumber you sound explaining it. Stokes theorem, yeah, that's how if you draw a loop around something, you can tell how much swirly is in it. So what do you mean? Is that what Stokes is about? Absolutely, that's what it's about. Let's go back to one of these problems that I told you the interpretation of it was when I was drawing the little paddle wheel. So over here, if you dropped this portion of a plane into a jacuzzi, you know, and you saw your paddle wheel, it'd be the swirly, the paddle would be, spinning around. That's how much swirly is in it. That's the circulation. Of course, when you're explaining swirly or circulation, a little paddle wheel swirling around, and somebody else is going to go, huh? What the heck are you talking about? And you can go, okay, just take a calculus 3 class, all right? You'll understand it. Oh yeah, you know how that is. Kobe says that's exactly how I explain what I'm studying to my family. I'm sure that's what happened around Thanksgiving dinner, right, folks? And that concludes the vector calculus module of this course. Congratulations.